until recently, I didn't even know there was a definition of a discriminant. I just thought it was kind of an ad hoc thing you could find by completing the square in the quadratic case. But we're going to go through a situation where we present a definition for any polynomial. And I'm going to just go through a few basics here. Like we're talking about the roots here, R1 and R2 will be roots, not necessarily distinct. If you take them by the factor theorem, a root corresponds to a factor. That's just because you get 0 out of it, if you write it in a linear fashion like this. All right. Now, when you multiply this out, you get x squared, and then minus the sum of the roots present as the coefficient of x, r sub 1 plus r sub 2. Notice I'm using subscripted variables because we're running out of letters. A lot of times you see people use a and b, but there's an obvious collision there. All right, and then plus the product R1, R2. So the product of the roots present as the constant term. All right. Now the reason why I took the time to do that is, I had it here anyway, but it's convenient to divide through by a because you do get an equivalent equation. Any solution to this would be a solution to this. There's no doubt about it. All right. And so we can see right here that minus R1 plus R2 is equal to B over A. And then the product R1 times R2 is C over A. That's handy here because we have a definition here. This is fairly cool. All right. Now notice that this definition right here, it has pairwise the difference of the roots squared, and that you're taking the product. And the reason why that's important is because if any of the roots are equal to each other, this is automatically 0, and we know we have a repeated 0. So that's kind of the motivation for this definition. This part right here, I guess, is sort of obvious. You have the coefficient a decremented by something here. But anyway, this part right here is what we're going to go with. And let's look. Delta is the symbol they use. And y'all, all I did here, this is just directly from this definition right here. You can see the product. That's kind of hard to see here. It's the product. And then preceding the product, you have the leading coefficient raised to this power 2 n minus 2. All right, and again, I have it directly right here. And notice that there's only a single pair of roots, so this product is almost empty. This product down here, this pi product, just has a single pair of roots. If it was a cubic, you would have 3 pairs of differences squared being multiplied, okay? So anyway, the rest of it's fairly self-explanatory. I changed this to a squared. And this part right here is a little, the main step that had teeth is the step that goes from here to here. Noticing this is what makes it fly. R1 plus R2 quantity squared is equal to R1 squared plus 2R1 R2 plus R sub 2 quantity squared. All right, so you have to subtract off 4R1 R2 to make this happen, folks. Again, if you don't believe me, just expand this out, subtract this off, and you'll see you get exactly this parenthetical quantity right here. Okay? So now we're at this stage of the problem where we actually see the coefficients popping into existence. And you can see right here this minus b over a would become positive, and you would a squared over this a squared, so you would just end up with b squared right here. And what I did, folks, is just this a gets squared, so it cancels with this a squared, the minus sign goes away. And then we have minus 4ac, and this is the infamous discriminant for the quadratic case, for the second degree case. And it's an important thing because when you do set it equal to, it's either going to be greater than 0, equal to 0, or less than 0 by trichotomy, and you get 3 different root conditions. You get 2 distinct real roots, you get a repeated real root, or you get distinct complex solutions, okay? But the cool thing about this is we've just this is just the tip of the iceberg. You notice that this definition holds for an arbitrary n. Okay, so you could use this definition to find the cubic discriminant and so on. Now it gets nastier and nastier. This one wasn't particularly ugly because we only had this single difference of 2 roots, right? There's just 2 roots. And so that was fairly easy, but you would have to, in the cubic case, this product here would have had 3, for the cubic case, there would have been 3 factors, or 3, I'll just put 3. In other words, you would have R1 minus R sub I minus R sub j happening 3 times. Basically, because there's 3, choose 2 ways you can pluck 2 factors from 3 factors, right? So that's actually equal to 3. In other words, hopefully this was that the 3 choose 2? Binomial coefficient 3 choose 2. There's 3 ways to pluck 2 marbles out of a bag of 3 marbles. And it's the same sort of thinking right here. You have 3 roots, and you'll end up with 3 differences in the same sense. Okay. So anyway, this we proved this by the definition of the discriminant, which is something that was unknown to me until probably, I knew a discriminant existed for every polynomial, but I never had actually looked at the definition of the discriminant. Okay. Now, up here, you can compare what would have happened right here. If you just complete the square right here, this is what's taught in every college algebra class in the world. If you just complete the square right here, you'll end up getting the radical, and the radicand itself is the discriminant. Okay, and that's the standard way of doing it. So this is kind of refreshing from where I stand to actually use this to find a super well-known famous result. Okay, that's all. Thanks for viewing.